of this morning session, Professor Quan Li from Chinese University of Hong Kong. So Professor Quan Li is the professor at the Chinese U of Hong Kong, and her research interests include functional materials and the structures for energy and biomedical applications and quantum sensing. Her work on energy materials focuses on electrode materials architecture development for batteries in investigating nanobio interfaces. Her group works on manipulating the interplay of nanoparticles and the biological system, as well as nano-vising development. Her work of quantum sensing is devoted to sensor development and applications in both energy storage and biomedicine. So now let's welcome Quan Li. Her talk today is the surface texturing of alkaline metal for enhanced cycle stability in battery electrode applications. So now let's welcome.
Thanks, Haital, for the very nice introduction. And also, I'm very grateful and honored to be included in this 85th anniversary of PolyU, and glad to have this opportunity to share with some of the recent development on the surface texturing of alkaline metals for enhanced cycle stability in metal battery electrode applications. So I have a not very small group, but only not a lot of students working on the energy storage materials with focus on the battery electrodes. And the research I shall be discussing in the following talk is mainly carried out by student Xitao Hu, and also work is in collaboration with Professor Biao Zhang and Dr. Yao Gao in Polytechnic University, and also Professor Le Shi in Xi'an Jiaotong University. We're also grateful to quite a number of constructive suggestions from Shirley and as well from Zijian. So to get to the stories, we have this inspiration coming from the observation of special growth characteristics of lithium metal in electrochemical process. In this trace group, it's probably the first to report the preferential 110 orientation of lithium metals in some specific electrolytes. And they also use the cryo microscope to see that the 110 direction of lithium is actually the slowest one to be grown when the lithium whisker grows, right? And 2 years later, in 2019, Gu et al. Inferred from some theoretical calculations that lithium 110 can actually be grown on copper 100 substrate, although in that work, there's no special experimental evidence of that such epitaxial growth is formed, but they used the system for battery tests and did show improved cycle stability of the performance. Then most recently, the preferential lithium 110 texturing has been demonstrated by electroplating lithium on copper substrate at extremely large capacity, and that was done by Archer's group. And the understanding of the specific growth pattern in terms of crystallographic orientation and improved cycle performance was tentatively ascribed to the lowest surface energy associated with the lithium 110 plane in these previous works, until a thorough theoretical investigation was published in 2020, in which Hagapi et al. Used density functional theory calculations and highlight the thermodynamic origin of the epitaxial, mossy, and fractal growth. These patterns are actually linked with the intrinsic energetic properties of the metal surfaces. And in their calculation, they did include the lithium and sodium metals, as well as magnesium as the alkaline metals. And they also found that the lithium 110 plane is thermodynamically more stable than other surfaces such as the lithium 100 in the electrochemical environment of lithium metal batteries that commonly adopted electrolytes such as ethylene carbonate or others. They also show that such a plane is associated with the lowest surface diffusion barrier for lithium. So how good would the theoretical prediction work, right? The first demonstration experimentally was actually not coming from the alkali metals, but from the zinc system, which took a hexagonal structure. There are, up to date, there are actually quite a number of works on the preferential texturing of the zinc system, but the earlier and representative work was done by Liang's group. They did show there are a number of benefits associated with the zinc OO1 orientation, which is the basal plane of the hexagonal zinc. And these benefits include the reduced parasitic reactions, such as the hydrogen evolution, and improved corrosion resistance, and most importantly, suppression of the zinc dendrite growth. Then the question comes back as would the theory actually work for alkali metals, which is our interest. Now, after all, the crystalline structure of alkali metals, as I'm shown here, is a body-centered cubic, and that is different from the zinc, which is hexagonal. So by that time, we were actually worked on the system for a while, but then this field is definitely a field with a lot of revolution as well as with involutions. Progress were made fast, right? By the end of 2021, there's a work published by Archer's group. They show that the lithium 100 preferential orientation can actually be prepared by a simple mechanical preparation process, right? Nonetheless, with the prepared lithium 100, the electrochemical property of the device is not exceptional, but then this is kind of expected based on the theoretical calculations by Hagapian, as 100 plane of lithium is neither of the lowest surface energy nor lithium surface diffusion barrier. So what is lithium 110 texturing, and can we do that? The answer is definitely yes. Although if you check in the literature, the theory was already there, although the previous experimental works are mainly on the iron-based materials such as the steels. But the theory was actually developed back in 1970s. They tell you the specific texture in the BCC metals can be developed, right, by activation of special slipping systems. Now here I put down a schematic showing the three major slip systems associated with the BCC metals. So the blue planes are the slip planes, and the slip direction is the 111 direction. Here we have 100 plane, 112 plane, and 123 plane as the most likely happen slip planes, right? And what happens is that the first one, the 110, 111 slip system, turns to be the easiest one among all to be activated at relatively low stress level. So what you have to do is to apply a stress to the system. Then by activating the slip systems, right, if this one is the main one, you will be able to obtain a formation of dominant cubic texture of 100. So this is lithium 100. Right now, of course, if the stress is too low, it's not working. And if it's too high, it's not working either, because by then you will be able to activate other slip systems, and this cubic texturing will no longer be dominant. Another common texturing that is known in the BCC metal is the shear texturing, also known as the Gauss texturing. And to obtain the Gauss texturing, it is a bit more complicated than the cubic one because the formation of the shear texturing relies on activation of multiple shear systems, right? And bad news is that by using the shear stress, you would be only getting a certain amount of shear textures, but not all. But then the good news is that the shear texture grains, once formed, is associated with the lowest stress level and lowest defect density. So if you will be able to initiate a recrystallization of the system, and that will lead to the growth of the shear texture, that is the texture of 110 orientation at the expense of the other grain of different texturings. And that will eventually lead to the dominance of the shear texture of 110. So that's the general theories. Though in the earlier literatures, there's no experimental protocols, then we take a bit of time to see whether we can work it out. So we took a pristine lithium foil that is commercially available. And the first trial is quite straightforward. We know by applying certain stress to the system, we would be able to activate the 110, 111 slip system, and that will give you the cubic texture. So we did. By using a hydraulic press at a pressure of 5 micropascal, we were able to generate this very nice 100 texturing of the lithium, as shown here. Right, this is the as prepared. You see a preferential X-ray diffraction from the 200 planes, telling you we obtained the texturing of the 100. 100. And this structure is quite stable. Here's the data. When the sample is stored in the glove box for 30 days, it actually can be longer. It stays for a month. Until now, it's still very stable. Right. To estimate the thickness of such a surface texturing layer, we did stripping experiment. Right. So the samples are stripped at the current density, at different current density. At the current density of 1 milliamp per centimeter square, but at different capacities, and 1 milliamp hour capacity corresponding to about 5 micron thickness of the lithium in the current experimental setting. So what we show is that we consider a specific crystallographic orientation of HKL. In this case, it's the 100 as the dominant one, when all the other diffraction intensities takes less than 20% of the total. Right, so up to here, we still have very good dominance of the lithium 100. With that estimation, the thickness of the surface texturing of lithium 100 is known as about 50 macrons, but that hasn't taken into consideration of the X-ray attenuation depth. So if that is taken into consideration, we would have at least 100 microns of lithium 100 on the surface of the lithium foil. Now, as said, the preparation of the lithium 110 is what we hoped, right? But that takes a bit more effort. The preparation process takes into 2 steps. The first step, following the theory, is just to use the shear stress and create certain amount of shear texturing in the sample. So we did. By pre-rolling and scraping the sample, we're able to get some of the shear texture grains in the lithium foils. And after that, we need the recrystallization process to get the dominance of the lithium 110, right? And that we did. And here is the results, right? So A is the one with the pristine lithium foil, which have a random texturing, and B shows the preparation results after the pre-rolling and the scraping. So that is to create certain amount of shear texture. You see the dominance of the 110 diffractions in the X-ray pattern, right? And the last stage is to initiate the recrystallization process of the material, and that will give you the dominance of the 110 texturing, right? And I have to say that the temperature for the recrystallization is very, very important, as shown in the XRD results in here. So at low temperatures, if the temperature is getting lower and lower, you see predominance or prevalence of the 200 diffractions in the X-ray. But if you move to even higher temperatures, you see the diffraction of the 211 start to grow. And only at about 75 degrees, right, we will be able to get a very nice surface texturing of lithium 110. And then again, by similar method, we estimate the thickness of the surface texturing is about 100 microns without considering the X-ray attenuation, right? So this is thicker than that one. Now, with that, we now have three different samples. One sample is the pristine lithium that are purchased, right? And the other two sample is what we prepared. One is the lithium 100 preferential texturing, and the other is the lithium 110, right? And one interesting fact to be pointed out for the pristine lithium FOIU, I don't know, for so many people working on the lithium metal electrode, if this has been noticed. If you look at the X-ray diffraction pattern of any one of each one of the lithium FOIU work on, you will see all the patterns in terms of the diffraction intensities among these peaks will be different. So there are a lot of variations in these samples, right? And then in terms of the surface, we did clean the samples with TH solution of naphthalene. So that removed the surface oxide and result in a smooth surface. And they're very similar for all three different samples, right? We did have a bit of more etching on the surface of the sample to see the grain boundary. So the size of the grains can be estimated as well. So for three of the samples, the pristine, lithium 100 and lithium 110, the grain size are in the range of hundreds of micrometers. So they're actually very similar as a starting sample, right? And again, we did XPS to look at the surface chemistry. For all these three samples, the surface chemistry are very similar as well. It contains a small amount or trace amount of lithium oxide and lithium carbonate, but then the chemical composition are almost identical for the three starting samples. Now, the important part, how does the electrochemical property associated with all these different samples? And again, for the pristine samples, we have a number of tests, right? And for each of the cells assembled with the pristine lithium FOIU as the electrode, we obtain somewhat different behaviors. At the very beginning, we thought this must be, we're not technically through this thing. So we tried many times, but then we see a lot of variation in the lithium FOIUs. With long-lived ones, you can cycle at 1 milliamp per centimeter square with a capacity of 1 milliamp hour per centimeter square. This lasts to about maybe 300 something hours, right? But with very short lived ones with only tens of hours, right? But then if you look at the symmetrical cells prepared with either lithium 100 or lithium 110, the results are actually very consistent. So for each of the FOIUs prepared as electrode in the cycloid, you get very similar results. The red one is the 100 and the blue one is the 110. And the blue one does last a lot longer in comparison with the 100 as well as the pristine samples. And one interesting pattern when observed is that for the pristine samples as well as the 100 samples, when the cell fails, you see these huge fluctuations in the voltage and suggesting the failure, the major failure mechanism is the cell shorts, basically. But then in the case of the lithium 110, what we see is that we never see these large fluctuations, or we seldom see these large fluctuations. We see, instead, we see a gradual increase of the overpotential until eventually the cell fails at longer cycles. We also have the test of the symmetrical cells at high current densities of 5 milliamp per centimeter square. And again, there are similar result obtained. The blue one, which is the lithium 110, that is showing much better performance than the lithium 100. Right, and further electrochemical calculations, including EIS and table test results are shown here. And we have 3 samples compared, and those are cycled at first cycle and the end of the 50 cycles. So for the 3 samples, we see very similar result in terms of the resistance of the bulk, right? And this is making sense because we don't expect the different surface texturing would affect the conductivity of the metal FOIU at all. But then in terms of the SEI resistance and the charge transfer resistance, there's quite a bit difference. But all 3 samples have similar trend. As you move from the first cycle to the 50 cycles, you see a decrease in both SEI resistance and the charge transfer resistance for all samples alike. But then among all of them, the lithium 110 is always associated with the lowest SEI resistance and the charge transfer resistance. Now, for the test, we see the exchange current density. At the first cycle, there might be a little bit difference among the three samples. It seems that the lithium-110 is slightly higher than the others, but the difference is not significant until later. At the end of the 50 cycles, you see this exchange current density of the lithium-100 is much higher than the rest, suggesting the lithium plating, the stripping is a lot easier to take place on the lithium-100 sample in comparison with the other two. Right, and how about the full cell performance? And here I shown again, for the pristine lithium samples without any preferential texturing, the result varies, right? We have slightly longer lived ones and short-lived ones, and it's always there. And in comparison with the lithium-100 and the lithium-110, you see the 110 is definitely performs a lot better than the 100. We have capacity retention maintained at about 96% at the end of 400 cycles. Then we'll also look at the rate performance of the cells. So in comparison with the lithium-100 and the lithium-110, we see the two cells are similar, actually at low rates. But then if you increase the rate to 5C, the difference in between the two becomes obvious. And also we show that in the voltage hysteresis at low rates, right? The behavior of the lithium-100 and 110 are very similar, but then we increase the rates to 5C. The hysteresis of the lithium-110 is smaller, right, than the 100. Right, then you will ask, if that's the case, do we have a full cell performance at a higher rates? Yeah, we do, and the very similar result were obtained. The winner is the lithium-110, and we do see initial capacity about 103 milliamp per gram with about 95% retention at the end of 500 cycles and at about 85% retention, capacity retention at the end of 800 cycles. Right, to understand why lithium-110 performs a lot better than the other surfaces, right, we carried out a little bit more surface iterations of the samples after recycling. Now, here is the results summarized from the XPS at the end of first and the end of the 50 cycles. When you compare the results from the lithium-110 and the 100 sample, you see there's not a lot of difference, but then if you look at the composition of the fluorine and also the lithium, you see the lithium-100 are actually of higher content for both elements, fluorine and lithium. And this difference actually becomes more substantial when you look at the results at the end of the 50 cycles. So here's a chart making comparison. For the lithium-110, we actually have a higher amount of organic components and a less amount of inorganic at the end of both the first cycle and the 50 cycles. And more importantly, we do see more amount of the lithium fluoride forming in the lithium-100 instead of lithium-110. And this is a bit, at the first glance, this is a bit counterintuitive to understand, to have an understanding on the electrochemical performance resulted. Because in the literature, there's a lot of arguments saying that you wish to have more lithium fluoride in SEI, which is more stable, which was resulting in more stable behavior of the electrode. But then if you dig into the literature a little more careful, and you will see this is arguable, as shown actually in a few number of works, and including a very representative ones by Shirley. I think they have one with Gu in South Type recently, by the end of last year. They did show that other than the composition of the SEI, the spatial distribution of these compositional elements is also very important in determining the SEI properties, including the iron flux properties as well as the stability with the electrode. But nevertheless, all right, we don't have further characterizations in this regard due to the lack of capacity in carrying out these experiments with the help with cryo-FIB and also cryo-TEM. But we're very much looking forward to collaborations with parties who have the capacity to carry out these experiments. Right, and along with cycles, we do see some evolutions of the texturing as well. So the red one is the lithium 100, the blue one is the lithium 110. As you shown here, this is a set of X-ray data, right, taken along with cycles. And this one is the initial cathode, right, without cycling, and by the way, it's a symmetrical cell. And this is the cathode, which is stripped in the first cycle. And this is the anode side, also in the first cycle, which is get plated. And for the lithium 100 sample, you see there's a bit of other intensities coming off, even at the end of first cycle. And this becomes more obviously if you cycle on. And at the end of the 300 cycles, you see the dominant diffraction become the 110 instead of the 200. So that is to say, the surface is losing its original texturing of the 110, and eventually it moves into 110. Now, in comparison, if you look at the lithium 110, this diffraction is stable towards the end. That is to say, along with cycles, the texturing is not changing at all. We also look at the surface morphologies using SEM. And to our surprise, right, although this pitting is known a long time ago, we didn't expect to see such a huge difference on the lithium 100 and the lithium 110 surface, right? So this is a cathode side at the in the first cycle, so first half of the cycle, the cathode gets stripped. You see obvious pits are formed on the surface, but in the case of 110, you see none, right? They're very flat. Right, and on anode side, the difference is not very obvious, right? Both of them have some plated lithium, and you may argue this one is slightly denser than this one, but I would say the difference is infinitesimal. Now, the pitting is also happened on the pristine lithium foils, and here's one of the images shown. Similar phenomena were observed if we cycle the symmetrical cells at higher current densities of 5 milliampere per centimeter square, right? Although the evolution is getting just faster. For the lithium 100, it still evolves, right? Eventually to sort of a dominance of the 110 diffractions, but eventually the 211 also grows. But then in the case of lithium 110 sample, you see this prevalence of the 110 diffraction always lasts towards the end, right? And in terms of the surface morphologies, similar results are observed. But then even for lithium 110, you see a little bit of pitting start to occur at high current densities. But then the density is a lot lower if you compare to the lithium 100. Now, in the second half of the first cycle, so what happens is that the anode side that was get plated now gets stripped, and the cathode side that gets stripped now get plated. Now we see very consistent results. The pitting process that occurs at low current densities occurs only on lithium 100, but not on the 110. But then at high current densities, both happens, but the density of the pits is much higher, right? And the slight difference in the cathode side that is plated, right? Now, at this point, you'd say, but the plating of the two are not much different, which is true. But you think of the plated lithium that sits on the pitted surface, you would imagine these holes may not be filled. Of course, that will rely on three-dimensional SEM image as shown by Shirley in the earlier talks, and which we have the two to do that. Then if the defects is to be accumulated, then you would expect to see a lot loose layer formed on the lithium 100 in comparison with the lithium 110. And such accumulated defects actually start to appear if you look at the SEM of the surface at longer cycles. So this is a symmetrical cell possessed at low current density, low capacity at the end of 50 cycles to 300 cycles. And you see for the lithium 100, the surface gets very, very rough. But then for the lithium 100, it's still quite flat. And similar results are obtained for symmetrical cells possessed at higher current densities, right? For the lithium 100, you see always very flat surface, but then these are rough surface appeared. How to understand this? So we actually did a bit of the modeling on this in collaboration with Lution in Xi'an University. And we used the SLAP model of lithium 100 as well as 110 with 10 to 15 angstrom of vacuum layer. And we used the density function theories to calculate. And we actually have two models, right? So in the first model, we construct a cone surface by removing half of the surface lithium atoms. So we create a cone that is a pit, right? And in the other model, we use the so-called plane model. We also remove half of the lithium surface atoms, but then they're randomly removed, so the surface is rather flat. Right? Then we look at the difference when asking these surface for the lithium 100 and lithium 110, right? To after a 2 picosecond ab initio molecular dynamics. And this is what we show. We see that in terms of the plane model for both the 100 and the 110 surface, they're actually very similar. So they remain kind of flat. But then for the cone model, in the case of lithium 100, the cone remains here, although it might get a little bit shallower. But then in the case of lithium 110, the cone is almost filled by the surface atoms of the lithium. So a quantitative result to describe this process is shown here. This is to tell in the surface of the lithium when the pit or surface roughness is created, the neighboring surface atoms of lithium or even the bulk one may diffuse into the pit or the roughness to fill it out, so to remove the roughness of the surface, right? And this is the result coming from the lithium 100 using the mean height, which tells you whether the pit has been fit, remains similar. So that means the pit is there. There's not much difference in the mean height. But then in the lithium 110, you see a decrease of the mean height that's corresponding to the process that pit has been filled. We also compare the potential energy of the cone, which is the green, dark green, and plane, which is the light green, for both the lithium 100 and 110 planes, right? And in both cases, we see that the plane, the potential energy associated with the plane is lower than that of the cone. But then at the end, you see when the pit of the surface is filled, in the case of the lithium 110, these two potential energies start to merge, right? Telling you they try to regain a flat surface. But then in the case of the lithium 100, there's not much difference, not much change. Telling you the pit once forms tends to be remain in there, right? So this is the message. This is the take-home message: is that in many cases we look at the plating or we focus on the growth process of the lithium on the substrate. But here the idea is that when the surface roughness is created, right, it can be created during stripping, it can be created during plating, but once it's there, the lithium 100 surface actually have the intention to flatten out by itself, but that does not exist in other surfaces such as the lithium 100, right? And that's probably the so-called thermodynamic origin of why lithium 110 surface is a better one, right? But then an interesting piece of result I'd like to show you is that if we carry out the cycling at high capacity of 5 milliamp hour for the symmetrical cell, of course, the performance would decay, right, at large capacity. But then still, the lithium 110 is the winner to the last. It performs a lot better than that of the pristine sample, the lithium 100 sample, right? But then if you look at the surface, right, for both lithium 100 and 110, right, at such large capacity, on the cathode side, when stripped, the pit will be formed. But then this pit on the lithium 110 did appear to be much shallower than that of the lithium 100. But then it does form. What does that mean? Our understanding is that the Haggapian's work really tells you the lithium 110 surface or the alkali metal 110 surface is a better one, is of thermodynamic origin. So when you are at an electrochemical process close to the thermal equilibrium, this benefit will be obvious. But then if you are kind of getting further away from the equilibrium, or you have the kinetical factors taking to the dominant role, or you have accumulated defects that cannot be compensated by the benefit brought by the thermodynamic reasons, right? You start to suffer. So the performance starts to decay. And a possible solution is that to include other strategies to work together with the approach of the lithium 110, right? That might bring in more advanced performance of the electrode and thus the batteries. Right, and we have also been asked a question. So the other results I show are in the carbonate electrolyte. So does it work also for other electrolyte? It does, right? So we tried ether, and it actually works a lot better in ester electrolyte for obvious reasons. We have these cells, symmetrical cells, performed at low current densities, all right, low capacity, and mid and high current density, low capacity, and also high current density, high capacities, right? In any of the cases, you see very good performance associated with the lithium 110, right? Much superior than that of the 100, right? So these are the cycles enlarged towards the end of the cycles, right? I think I'm running out of time, so I'll be brief on the next ones. Just want to show you the method that we developed is very, very general. It applies to all alkali metals. So we tried sodium and potassium as well, and we got the preferential texturing of sodium 110, 100, and potassium 110 and 100. And for the sodium battery, we have a quick run. You see the symmetrical cells and ester electrolyte, and the full cells, right? It's always the winner will go to the 110 plane, right? So to conclude, that I hope I've shown you that we developed a generic method to prepare the textured alkaline metal for use. And we did obtain superior cycle performance of the 110 texturing, and that is understood by the uniform stripping and dense plating associated with such a plane with a thermodynamic origin. And of course, this is an ongoing project. There's not new questions and new problems which are challenging, and we are lack of characterization tools, right, to understand the whole process. And we're very welcoming collaborations in this regard. And with that, I would like to end my talk and answer your questions. Thank you.
Thank you, Professor Lee, for your wonderful talk. So now we have time for a few questions. Professor Sherryman, please ask your question.
The clapping, there was it's really nice to see the universal rule, I guess, for sodium, potassium, and lithium all observed the 110 as the thermodynamically stable surface. Just a quick suggestion. I think trend the 100, because the X you identify the texturing through XRD. Yeah, I think by the selection rule, I think you have to make a choice using 200. I don't know if the reviewers give you trouble because they have this X-ray selection rule. They insist us using the BCC.
Right. We're actually asked. So we say
not me, okay, yeah. But I can guess.
Right. So this is you can look at the old crystallography. They say, right, it's a 100 or 110. That's fine. But then for this BCC metal, you know, by definition, you're choosing a non-primitive cell. So
yes.
100 will be missing. You only have 200, right?
Yeah. So yeah, that's just a quick comment. My question is really like when you measure something is around 100 micrometer, right? The texturing. Yeah. So yeah, I was just wondering that you know, I think in a lot of the current effort in battery 500, we try to lower the thickness to 40 to 50 micrometer. And over there, I don't recall we saw any preferred orientation. And of course, I don't know what method they used for fabricating those film. I just wonder, in your method, do you have the capability of maintaining the texturing when the thickness below 100 micrometer?
Right, in principle, it can be done, right? Currently, we don't have the capacity. The reason why is that all the samples are prepared by hand at the moment, right?
Okay.
So we do a pre-rolling, the scraping by hand, and then we do annealing. So annealing is generally fine. It doesn't matter how thin the foil is, right? But then because you have to hand perform this when the foil gets very thin and very easy to break. But then the next stage, we hope we can get to a bit of automation with the machine helps, right? In that case, you don't like rely things on your hand, right? So you have support, right, on the substrate and by the machine. Then hopefully this can be reduced to maybe 50 microns or even thinner, right? And the other idea is we had a discussion last time with Zijian, that we might be able to incorporate these things onto a 3D mesh or something to give actual support, right? So in that case, because our current problem is the mechanical strength, in that case, we might be able to get a very thin foils forming on the surface of the metal mesh, and that have only a thickness of about maybe 50 microns or even thinner.
Mm-hmm. Mm-hmm. Yeah, and I also agree with you. The SEI, organic or inorganic, is not the key. It's how these species are distributed. So it's very fascinating to see you do have a thin inorganic layer, but it's quite stable in 110.
Exactly. So we looked around in Hong Kong. Actually, even in the whole Hong Kong, currently we don't have a facility that can look at that integrate the cryo fib with the cryo TM. Although PolyU, they have a cryo fib and they have a cryo TM, but they don't have the sample transfer.
Yeah,
holder
it's called a clean connect.
Right.
Yeah, they just review the Thermo Fisher just reviewed the product in IMLB this week, so I can connect you to the people to ask about the
right. Yeah. So we're very much looking forward to a party who have the capacities, if that can be done. So this will be a very interesting sample to look at, because we in the carbonate system we have a very little amount of inorganic materials, but then the performance, it looks a lot better.
Yeah, I'm done. Thank you.
Thanks.
Okay, so we can have one more question. So any question from others? Okay, if no more question, then we'll end this morning session. So thank all the speakers for your great talk.